Right now, something ancient is racing past our sun. You can't see it with your eyes. Most telescopes can barely catch it. But it's there. A visitor from another star, carrying secrets older than human memory. We thought we were alone in our corner of space. We were wrong. The universe has been sending us messages all along. Silent travelers, cosmic refugees, fragments of worlds we'll never see. These wanderers have a name: interstellar objects. Think of them as pieces of broken worlds, ejected from star systems so far away that their light hasn't even reached us yet. They drift through the dark spaces between stars, spaces so cold and empty that nothing moves, nothing changes for millions of years. And then, once in a lifetime, one of them finds our sun. The history of these visitors is incredibly short. We only noticed the first one in 2017. It had a strange name, Oumuamua. That's Hawaiian. It means scout or messenger, and it lived up to its name. Oumuamua was weird. It looked like a rock, long and thin, tumbling through space. But it moved in a way rocks shouldn't move. It accelerated. It sped up without any visible rocket pushing it. Scientists are still arguing about what it really was. 2 years later, in 2019, the second visitor arrived. This one had a more familiar name, Borisov, named after the astronomer who found it. Borisov was different from Oumuamua. It looked like a comet. It had a tail. It released gas and dust. It behaved exactly like the comets we know from our own solar system. But here's the thing. It wasn't from our solar system. The chemicals inside it, the frozen gases, the ancient ices, all of it came from another star. Now, in 2025, the third confirmed visitor has crossed our sky. Its name is 3I/ATLAS. The I stands for interstellar. The ATLAS is the telescope system that found it, a network of robot eyes scanning the sky every night for dangerous asteroids. But this time, ATLAS caught something that wasn't dangerous. It caught something precious, a messenger from deep time. When astronomers first spotted 3I/ATLAS, it was incredibly faint. Imagine trying to see a birthday candle flame from 100 miles away. That's how dim it appeared. It registered around magnitude 17 or 18 on the brightness scale. For comparison, the faintest stars you can see with your naked eye are magnitude 6. This visitor was thousands of times dimmer. It barely showed up at all, just a fuzzy smudge against the background of distant galaxies. This faintness tells us something important. Either 3I/ATLAS is very small, maybe just the length of 2 football fields, or it's extremely inactive, barely releasing any gas or dust. At the time of discovery, it was still far from the sun, drifting in the cold outer solar system where sunlight is weak and temperatures hover near absolute zero. Out there, nothing melts, nothing changes. The object was essentially frozen solid. But here's what makes 3I/ATLAS truly special. It's not unique. In fact, it's incredibly common. You see, we've only managed to spot 3 interstellar visitors so far. 3. But scientists estimate that on any given day there are 10,000 interstellar objects passing through the inner solar system, right inside Neptune's orbit. 10,000 every single day. Let that sink in. While you're reading this, while you're eating breakfast, while you're sleeping, 10,000 fragments from alien star systems are silently drifting through our neighborhood. We're not alone. We've never been alone. We're constantly swimming through a river of galactic debris, and we barely notice it. The 3 visitors we've confirmed, Oumuamua, Borisov, And now 3I/ATLAS are just tokens. They're lucky glimpses, tiny beams of light cast upon an enormous invisible flow of cosmic traffic. Think of it like fireflies on a summer night. You see a few flashing in your backyard, but the forest beyond is filled with millions you'll never see. The faintness of 3I/ATLAS makes this even more amazing. It's a fleeting, minute representative of a vast population we can barely perceive. And it brings with it something even more incredible: the weight of deep time. Deep time. That's a term geologists use to describe timescales so long they break our brains. Not years, not centuries, not even thousands of years. Millions, billions. Time measured in the slow drift of continents, the birth and death of mountains, the rise and fall of entire oceans. 3I/ATLAS has been travelling for millions of years, maybe tens of millions. It was violently ejected from its home star system long before humans existed, long before dinosaurs walked the earth, long before the first fish crawled onto land. It drifted through the absolute cold and darkness of interstellar space, bombarded by cosmic radiation, etched by ancient photons from stars that may no longer exist. The interstellar medium, the space between stars, is not truly empty, but it's close. It's one of the most silent places in existence. Imagine the quietest room you've ever been in. Now make it 1 billion times quieter. That's the interstellar void. It's a silence like the bottom of the ocean, like the inside of a tomb, cold, dark, eternal. And 3I/ATLAS survived it all. It carried the radiation-scarred history of alien skies across unimaginable distances. And after all that time, after all that drifting, it chose our sun as its final stage. Not because it was aiming for us, not because it knew we were here, but because gravity brought it here. Because the chaotic dance of the galaxy nudged it ever so slightly onto a path that intersected with our tiny corner of space. Think about what this means. This object, this ancient frozen wanderer, is older than memory itself. It was born in a place we'll never see, under a star whose light hasn't reached us yet. It travelled through darkness we can't imagine. And then, for just a few brief months in 2025, it passed close enough to our sun that we could see it, we could study it, we could learn its secrets. It drifted in silently, older than memory, colder than any night. The significance of 3I/ATLAS goes far beyond its size or brightness. It represents a fundamental truth about the universe we live in. Our solar system is not an island. It's not isolated. It's not protected by invisible walls. We are part of a vast galactic ecosystem where matter constantly flows from star to star. Every star system is leaky. Planets form in chaotic environments. Gravity flings objects around. Some get captured into stable orbits. Others get ejected at high speeds, thrown out into interstellar space like cosmic refugees. Our own solar system does this. Jupiter, with its enormous gravity, regularly kicks comets out into the void. Those comets will drift for millions of years. Some of them might eventually find another star, another world, maybe even another civilization that will wonder where they came from. And the same process works in reverse. Other star systems eject their debris. Some of it finds us, some of it becomes visible, most of it passes unseen, but it's always there, always flowing, always connecting the stars in ways we're only beginning to understand. 3I/ATLAS is one thread in this enormous cosmic web, one messenger in an endless conversation between stars. And even though it's small, even though it's faint, even though it's fragmenting and dying as we watch it, it carries something infinitely valuable. It carries proof. Proof that we are not alone in the universe's vast machinery. Proof that the building blocks of worlds travel freely between stars. Proof that our sun is just one stop in an eternal journey that began long ago and will continue long after we're gone. Somewhere in the dark, the fourth is already on its way. But how do we know? How can astronomers look at a tiny dot of light millions of miles away and declare with absolute certainty that it comes from another star? The answer lies in something beautiful and precise. Mathematics, pure geometry, the invisible architecture of motion that governed everything in space. 3I Atlas was first spotted on July 1st, 2025. The Atlas telescope in Rio Hurtado, Chile, caught something moving against the background of fixed stars. At first, it looked like just another rock, another asteroid, another piece of space debris. But within hours, something strange became clear. This object was moving too fast. Way too fast. Think of it like this. Imagine you're standing at a train station. Most trains slow down as they approach. They follow predictable paths along curved tracks. They stop, turn around and come back. But what if one train came screaming through at full speed, never slowing down, never stopping, following a path that just kept going straight? That's what 3I Atlas was doing. When astronomers calculated its orbit, they discovered something that changed everything. A single number, a mathematical constant called eccentricity. In orbital mechanics, eccentricity tells you the shape of an orbit. It's written as the letter E, and it determines whether an object is trapped or free. For objects that belong to our solar system, planets, asteroids, comets, the eccentricity is always less than or equal to 1. These orbits are closed loops, circles or ellipses. Objects that follow these paths are gravitationally bound to the sun. They might take years or centuries to complete one orbit, but they always come back. They're prisoners of our star. But 3I Atlas was different. Its eccentricity was calculated at 6.75. That's not just greater than 1, that's massively greater than 1. This single measurement proved beyond any doubt that 3I Atlas was not from our solar system. It was following a hyperbolic trajectory, an open, one-way path. It came from somewhere else, and it will never return. Let that sink in. The math doesn't lie. An eccentricity greater than 1 means the object possesses hyperbolic excess velocity. This is the speed it retains far from the sun, the speed left over after fighting against our star's gravity. When 3I Atlas entered our solar system, it was moving at 58 kilometers per second relative to the sun. That's 130,000 miles per hour, faster than any rocket we've ever built, faster than any object naturally born in our neighborhood could possibly move. Compare this to the previous 2 interstellar visitors. Oumuamua had an eccentricity of 1.2 and a hyperbolic excess velocity of 26 kilometers per second. Borisov had an eccentricity of 3.4 and a velocity of 32 kilometers per second. Both impressive, both clearly interstellar. But 3I Atlas? It's moving nearly twice as fast as Oumuamua. It's the fastest interstellar visitor we've ever detected. This extreme speed makes its trajectory look almost perfectly straight. Most comets follow curved paths around the sun, looping in graceful arcs. But 3I Atlas barely curved at all. It came in, it passed the sun, It's heading back out. The path looks like someone drew a line through the solar system with a ruler. The discovery wasn't just a lucky glance, it required detective work. Within hours of the initial sighting, astronomers scrambled to find older images of the same patch of sky. They discovered that other telescopes had actually photographed 3I Atlas weeks earlier without realizing what it was. The Zwicky Transient Facility found images from June 14, 2025. Atlas itself found pre-discovery images from June 25th. By piecing together these observations, scientists extended the object's known trajectory backward in time. This is crucial. The more observations you have, the more accurately you can calculate an orbit. And accuracy matters. The difference between an eccentricity of 0.99 and 1.01 is the difference between trapped and free, between returning and never coming back, between solar system native and cosmic refugee. When they traced 3I Atlas's path backward, the math pointed to a specific region of the sky, the constellation Sagittarius, near the center of the Milky Way galaxy. That's where this wanderer came from. Not from a specific star. It's been traveling too long for that. Probably millions of years, but from that general direction in the galaxy. The trajectory also revealed something interesting. 3I Atlas's path is tilted 175 degrees relative to the plane of our solar system. That's almost perfectly backwards. It's moving in retrograde, which means it's orbiting in the opposite direction from all the planets. This is another strong clue that it's not from here. Objects born in our solar system tend to orbit in the same direction, because they all formed from the same spinning disk of gas and dust 4.6 billion years ago. On October 30th, 2025, 3I Atlas reached perihelion, its closest approach to the Sun. At this point, it was about 1.4 astronomical units away. That's 130 million miles, just inside the orbit of Mars. For comparison, Earth orbits at 1 astronomical unit. So 3I Atlas came reasonably close. Not dangerously close, but close enough for our best telescopes to get a good look. As it approached the Sun, gravity pulled on it. The comet sped up. It reached its maximum velocity at perihelion. Then, as it began moving away, gravity tried to pull it back, but gravity wasn't strong enough. The comet's speed was too high. It kept going. And it always will. On December 19th, 2025, 3I Atlas will pass Earth at a distance of about 270 million kilometers. That's 170 million miles, farther than the distance from Earth to the Sun. So there's no danger of collision, no threat. Just a brief opportunity to observe something incredibly rare before it disappears forever. The geometry of its path tells us exactly where it's going. After leaving our solar system, 3I Atlas will continue moving through the Milky Way at about 58 kilometers per second relative to the Sun. It will drift upward through the galactic plane, moving away from the galactic center. In a few million years, it might pass close to another star system. Maybe someone else will see it. Maybe they'll wonder where it came from. Maybe they'll calculate its orbit and realize, just like we did, that it's a messenger from a place they'll never see. This is the power of mathematics. A handful of observations, a few measurements of position and velocity, and suddenly we know the entire story. We know where it came from. We know where it's going. We know it will never return. The universe runs on laws so precise, so unchanging, that we can predict the motion of objects millions of miles away with absolute certainty. The hyperbolic trajectory of 3I Atlas transforms abstract geometry into a profound narrative truth. This object is not bound by our sun. It does not belong to us. It is a pathless wanderer, following a course determined by forces we barely understand, shaped by events that happened long before humans existed. It passed through our system the way a whisper crosses a dream, touching nothing, leaving only questions. But those questions have answers, and the answers reveal something heartbreaking about this ancient visitor. 3I Atlas is dying, and we get to watch it happen in real time. When astronomers first spotted 3I Atlas in July 2025, they immediately noticed something different from the first interstellar visitor. Unlike Oumuamua, which looked like a solid rock with no visible activity, 3I Atlas appeared fuzzy, distinctly fuzzy. It had a coma, a glowing cloud of gas and dust surrounding its nucleus. This was the signature of a comet, an active comet, and that meant it was releasing material. It was bleeding into space. Think of a comet as a dirty snowball, a mixture of ice and rock and dust all frozen together. Out in the cold darkness between stars, where temperatures drop to just a few degrees above absolute zero, everything stays frozen solid. Nothing moves. Nothing changes. The comet is like a time capsule, perfectly preserved for millions of years. But when a comet enters a solar system and gets close to a star, everything changes. The sun's heat begins to work on the frozen surface. The ices don't melt like water turning to liquid. Instead, they sublimate. They turn directly from solid ice into gas. This is the same process that makes dry ice create fog. Frozen carbon dioxide skips the liquid phase and becomes gas instantly. For 3I Atlas, this process began months before discovery. NASA's TESS satellite caught images showing the comet was already active back in May 2025, when it was still 6.4 astronomical units from the Sun. That's farther away than Jupiter. At that distance, sunlight is weak and temperatures are still incredibly cold. But it was enough. The most volatile ices, carbon dioxide and carbon monoxide, began to sublimate. As the comet got closer, the activity intensified. By July, when it was discovered, 3I Atlas was ejecting 6 kilograms of small dust particles every second, plus 60 kilograms of larger dust particles every second. That's 66 kilograms total, every second. Day after day after day. The comet was tearing itself apart. Spectroscopic observations revealed something extraordinary about its composition. The coma of 3I Atlas contains at least 16 times more carbon dioxide than typical solar system comets. This makes it one of the most CO2-rich comets ever observed. This extreme composition tells us that 3I Atlas formed in an incredibly cold environment, far from its parent star, in the frozen outer reaches of another planetary system. The carbon dioxide coma is enormous. Infrared observations from NASA's SphereX mission in August showed it extends at least 348,000 kilometers in radius. That's nearly the distance from Earth to the Moon. This massive cloud of gas is invisible to the naked eye, but in infrared light it glows brilliantly. The comet is surrounded by a sphere of carbon dioxide bigger than most planets. As 3I Atlas approached perihelion on October 30th, 2025, the sublimation became violent. The sun's heat bombarded one side of the nucleus, Frozen gases turned to vapor. The vapor rushed outward at high speed, creating jets. These jets acted like tiny rockets pushing against the nucleus. This created a non-gravitational force, an acceleration that couldn't be explained by gravity alone. Astronomers measured this force. It was significant, about 94 kilometers per day squared. That means every day the comet's velocity changed by 94 kilometers per day, more than gravity alone would predict. To produce this much acceleration, 3I Atlas had to be ejecting massive amounts of material. Calculations suggest it lost more than 13% of its total mass near perihelion. 13%. In just a few weeks. Imagine losing 13% of your body weight in a month. Now imagine you're made of ice and rock, and pieces of you are literally blowing off into space. That's what 3I Atlas experienced. The sun wasn't just warming it. The sun was destroying it. The fragility of 3I Atlas became devastatingly clear when the Hubble Space Telescope turned its powerful eye toward the comet. Images from October revealed something shocking. The nucleus had fragmented. It had broken into more than 24 distinct pieces. The comet that had survived millions of years in the frozen void of interstellar space couldn't survive a few months near our sun. Think about that. This object drifted through the galaxy for eons. It survived cosmic ray bombardment. It endured temperatures near absolute zero. It travelled farther than the human mind can comprehend. And then, after all that, it came close to a star, our star, and fell apart. The fragmentation occurred about 91 million miles from Earth. Close enough for Hubble to resolve individual fragments. Each piece is now following its own slightly different orbit. They're spreading out, creating a debris field. Some fragments are more active than others, releasing more gas and dust. Some appear darker, suggesting different compositions or different levels of radiation damage from the long interstellar journey. Why did it break apart? The answer lies in structural weakness. Comets are not solid objects. They're more like loose collections of ice and rock barely held together by weak gravity and frozen chemistry. When one side heats up and begins ejecting gas violently, it creates enormous stress. The pressure from sublimating gas pushes outward. If the nucleus is porous or has internal weak points or cracks, that pressure can overcome the material strength. The comet splits. 3I Atlas appears to have been particularly fragile, possibly because it formed under different conditions than solar system comets, possibly because radiation damage over millions of years weakened its structure. Possibly because its extreme CO2 content created more violent sublimation. We don't know for certain, but the result is clear. This ancient traveller sacrificed itself to give us knowledge. The composition of 3I Atlas differs from typical solar system comets, not dramatically, but noticeably. The extreme carbon dioxide abundance is unusual. The polarization measurements, the way light reflects from its coma, suggest a mixture of icy and dark material similar to trans-Neptunian objects from the outer edges of our solar system, but with subtle differences, chemical fingerprints that mark it as alien. Studying these differences is crucial. Every star system forms under slightly different conditions, different amounts of heavy elements, different temperatures, different radiation environments. These variables affect what materials condense and how they're arranged. By analyzing the composition of interstellar visitors like 3I Atlas, we can learn about planetary system formation across the galaxy. We can test whether the chemistry that created Earth is common or rare. As 3, Atlas continues its journey outward. It grows fainter. The fragments are separating. The coma is expanding. The tail, first visible in August as a faint 30 arcsecond streak, growing to 50 arcseconds by September, continues to stretch behind the retreating nucleus. This tail is made of dust particles pushed away from the sun by light pressure. Photons from the sun physically push the tiny particles, creating a glowing stream that points away from our star. By December 2025, 3I Atlas will pass Earth at 270 million kilometers. It will be visible through medium-sized telescopes for observers in dark locations. Then it will fade further. By early 2026, it will become too faint for most ground-based telescopes. By late 2026, only the most powerful instruments will be able to detect it, and eventually it will vanish completely, merging back into the darkness between stars. Even telescopes strain to see it, as if light itself hesitated to reveal a secret from another sun. The 3 confirmed interstellar visitors now paint 3 very different portraits. Oumuamua, the tough, mysterious rock that showed no cometary activity but still accelerated mysteriously. Borisov, the conventional, stable comet that behaved exactly like expected. And 3I Atlas, the fragile, chemically unusual comet that disintegrated under solar heat. This diversity tells us something profound. The galaxy is filled with every imaginable type of debris. Tough survivors, familiar strangers, fragile messengers, all of them wandering the void, all of them occasionally finding new stars. The 3 confirmed interstellar visitors now paint 3 very different portraits. But there's something haunting about the name we gave this third messenger, 3I Atlas, a designation that sounds cold and scientific. But hidden inside that name is a story older than science itself, a myth about weight, about burden, about holding up the entire sky. In ancient Greek mythology, Atlas was a titan, not a god, not a mortal, something in between. During the Great War between the Titans and the Olympian gods, the Titanomachy, Atlas fought on the losing side. And when Zeus and the Olympians won, they needed to punish the Titans. Most were thrown into the dark pit of Tartarus. But Atlas received a different sentence, a special punishment. He was condemned to hold up the heavens forever. Picture it, a giant figure standing at the edge of the world, arms raised, bearing the weight of the entire sky on his shoulders, never resting, never sleeping, never allowed to put down his burden, for eternity. The ancient Greeks imagined Atlas as the ultimate symbol of endurance, of carrying an impossible weight that can never be set down. But Atlas was more than just a punishment story. He was also considered the god of astronomy, the inventor of the celestial sphere. He understood the motions of the stars. He knew the patterns of the heavens. He was the guardian of cosmic knowledge, the pillar that kept the universe from collapsing. Without Atlas, the sky would fall, the cosmos would end. The modern Atlas survey, the telescope system that discovered 3I Atlas, carries this same mythic weight. It's an automated network of robotic eyes that scan the entire visible sky every night, looking for danger, looking for asteroids that might hit Earth, looking for unexpected visitors from the dark. It never sleeps. It never stops. It shoulders the burden of planetary defense. Think about the irony. The original Atlas was enormous, powerful, eternal. He held up the entire sky. But the comet we named after his survey, 3I Atlas, is tiny, fragile, temporary. Before it fragmented, astronomers estimated its nucleus was maybe 300 to 600 meters across. That's the length of 2 football fields at most. Compared to the cosmic scale of things, it's nothing, a speck, a grain of sand. Yet this infinitesimally small object carries an infinitely heavy burden, not a physical weight, an intellectual one, a philosophical one, the weight of questions, the burden of implications. Because 3I Atlas proves something that changes everything we thought we knew about our place in the universe. It proves that stellar systems are connected, that stars don't exist in isolation, that matter flows constantly between them, that the universe is leaky, porous, interconnected in ways we're only beginning to understand. For most of human history, we thought the solar system was our island, our castle, our home with walls that protected us from the vast emptiness beyond. Sure, we knew about other stars, but they seemed impossibly distant, separated by light years of absolute void. We imagined space as empty, silent, dead. But 3I Atlas and the thousands of unseen objects like it passing through our neighborhood every day proves that assumption wrong. Space is not empty. It's filled with travelers, messengers, fragments of broken worlds. The galaxy is alive with motion, with exchange, with constant traffic we never noticed until recently. This realization imposes a burden on us, the burden of expanded awareness, the burden of deep time, the burden of understanding that our sun is not special, our planet is not protected. We're just one temporary stop in an endless cosmic cycle that began billions of years ago and will continue billions of years into the future. 3I Atlas forces us to confront our own transience. It's been traveling for millions of years. It will continue traveling for millions more. Its journey dwarfs all of human civilization, all of recorded history. Everything humanity has ever built or thought or dreamed fits into a tiny fraction of this comet's existence. And yet, we're the ones watching it. We're the ones studying it. We're the ones trying to understand where it came from and what it means. In that sense, we become the modern Atlas, not holding up the sky with our bodies, but holding up the weight of cosmic knowledge with our minds. Every new discovery adds to that weight. We used to think our solar system contained 8 planets, some moons, and a bunch of rocks. Simple, manageable. Then we discovered the Kuiper Belt with thousands of icy objects. Then we found exoplanets around other stars, thousands of them. Then we detected gravitational waves from colliding black holes. Then we imaged the supermassive black hole at the center of our galaxy. Now we're tracking interstellar objects passing through our neighborhood. The sphere of human knowledge keeps expanding, and with it, the weight we carry, the burden of questions that need answers, the responsibility of understanding our place in something so vast it breaks comprehension. 3I Atlas is a mirror. When we look at it, we see ourselves, a small, fragile object traveling through an incomprehensibly large universe, temporary, vulnerable, carrying the accumulated damage of a long journey, moving on a path we didn't choose, unable to stop, unable to turn back. The comet's fragmentation makes this mirror even more poignant. We watched it break apart under stress. We saw pieces of it scatter, each fragment following its own slightly different path, separating, diverging, moving away from each other as they drift back into the darkness. Isn't that exactly what happens to civilizations, to species, to worlds, everything we build, everything we love, everything we think is permanent? Eventually it fragments, eventually it scatters, eventually it returns to the cosmic reservoir to be recycled into something new. The atoms in your body right now came from stars that exploded billions of years ago. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was forged in stellar furnaces, scattered into space by supernovae, incorporated into clouds of gas and dust, condensed into new stars and planets, and eventually assembled into you. You are stardust, literally, physically, the same stardust that makes up 3i Atlas, the same stardust that makes up every object in every star system across the entire galaxy. We're all made of the same stuff, all connected by the same cosmic cycle, all temporary arrangements of matter that will eventually scatter and reform into something else. This is the burden the comet imposes. The weight of understanding that nothing is separate, nothing is permanent. We are part of a vast machine that recycles matter and energy across billions of years. Our sun is both a collector and an ejector. Our solar system both receives visitors like 3i Atlas and sends out its own comets to other stars. Right now, somewhere in the galaxy, another civilization might be watching one of our comets pass through their system. They might be wondering where it came from. They might be calculating its trajectory. They might be studying its composition. They might be asking the same questions we're asking, feeling the same weight we're feeling. The universe is having a conversation with itself, using comets as words, using gravity as grammar, using chemistry as meaning. And we're finally learning to read the messages. 3i Atlas is one sentence in that infinite conversation, a brief statement from another star system, a message that says, we exist, we formed planets, we ejected debris, and that debris found you. It's not addressed to us specifically, it wasn't aimed at us, but we received it anyway, because the universe is always broadcasting, always sharing, always connecting the modern Atlas, us, humanity, with our telescopes and computers and questions, shoulders the burden of translating these messages, of understanding what they mean, of carrying that knowledge forward. It's not a punishment like the mythic Atlas endured. It's a privilege, a responsibility, a weight worth carrying. It reminds me that our sun too will one day drift through someone else's night. But before we lose 3i Atlas completely, before it fades beyond the reach of even our most powerful telescopes, we need to read the message it carries, because this comet is more than just a rock, more than just ice and dust. It's a letter written in atoms, composed over millions of years, addressed to no one in particular, but delivered by pure chance to us. Every object in the universe carries a chemical fingerprint, a unique signature written in the specific mix of elements and molecules it contains. This fingerprint tells a story about where the object formed, what temperature it experienced, what radiation it encountered, what kind of star it orbited, and by analyzing the composition of 3i Atlas, we're essentially reading a message from another planetary system, a system we'll never visit, orbiting a star we may never identify. The most striking feature of 3i Atlas is its extreme carbon dioxide content. Observations in August 2025, using NASA's SphereX mission, revealed that the comet's coma contains at least 16 times more CO2 than typical solar system comets. 16 times. That's not a small difference. That's a fundamental compositional distinction that tells us something profound about where this comet formed. Carbon dioxide freezes at very low temperatures, about 194 Kelvin or minus 79 degrees Celsius. In our solar system, comets with high CO2 content typically formed in the coldest outer regions, beyond the orbit of Neptune, in places like the Kuiper Belt or the Oort cloud. The abundance of CO2 in 3I Atlas suggests it formed in a similarly cold environment in its home system, far from its parent star, in the frozen darkness where only the most volatile materials could condense. But there's more in the coma than just carbon dioxide. Spectroscopic observations, the technique of splitting light into its component colours to identify specific molecules, have revealed a complex chemistry. Water vapour, of course. That's expected from any comet. But also carbon monoxide, methane, hydrogen cyanide. Each molecule tells part of the story. Hydrogen cyanide is particularly interesting. Observations from the James Clerk Maxwell Telescope in September 2025 detected HCN production rates of 1.5 kilograms per second on September 7th, climbing to 4.5 kilograms per second by September 14th. Hydrogen cyanide is an organic molecule, meaning it contains carbon. It's also one of the building blocks of more complex organic compounds. It's found in interstellar clouds, in comets, in the atmospheres of planets, and it's one of the chemical precursors thought to be important for the origin of life. Think about that. This comet, formed around another star, carries organic molecules, carbon-based chemistry, just like comets in our own solar system. The implications are staggering. The chemistry of life isn't unique to Earth. It's not even unique to our solar system. It's universal, spread throughout the galaxy, carried from star to star by wandering messengers like 3I Atlas. The James Webb Space Telescope made its first observations of the comet on August 6, 2025, using its powerful infrared instruments. Results announced by NASA on August 25th revealed details about the comet's temperature, its gas production rates, and the distribution of molecules in the coma. JWST's sensitivity allows it to detect molecules that would be impossible to see with ground-based telescopes. It can pick out individual chemical signatures in the infrared spectrum, the unique wavelengths at which specific molecules absorb or emit light. Hubble Space Telescope observations, scheduled for November 2025, will perform ultraviolet spectroscopy, analyzing the comet in ultraviolet light to determine the sulfur-to-oxygen ratio in the gas emissions. This ratio is important because it provides clues about the chemical conditions in the comet's birth environment. Different ratios indicate different formation temperatures and different elemental abundances in the protoplanetary disk where the comet formed. These observations aren't just about one comet. They're about understanding planetary system formation across the galaxy. Every star forms from a collapsing cloud of gas and dust called a molecular cloud. These clouds contain the raw ingredients: hydrogen, helium, carbon, oxygen, nitrogen, and trace amounts of heavier elements left over from previous generations of stars. When a cloud collapses to form a new star, the leftover material forms a disk around the young star, and from that disk, planets and comets condense. But the exact composition of that disk, the ratios of different elements, the temperature gradients, the density variations, depends on the specific conditions in that particular region of the galaxy. Different metallicities, different radiation fields, different nearby stars influencing the cloud. Each planetary system forms with a slightly different chemical recipe. By studying interstellar visitors like 3i Atlas, we can compare the chemistry of other planetary systems to our own. We can test whether the conditions that led to Earth were common or rare. We can determine whether the building blocks of life are universal or localized. We can start to answer the biggest question of all. Are we alone? The molecules detected in 3i Atlas, water, CO2, CO, methane, HCN, are collectively known as volatiles. They're called that because they easily evaporate or sublimate at relatively low temperatures. But there's another category of molecules that scientists are particularly interested in: complex organic molecules. Polycyclic aromatic hydrocarbons, or PAHs, and fullerenes, including the famous soccer ball-shaped C60 molecule called Buckminster fullerene. These molecules are often called atomic fossils. They're carbon structures, elaborate arrangements of carbon atoms that form in extreme environments, in the outer atmospheres of dying stars, in the shock waves of supernova explosions, in the dense clouds of gas between stars. They're incredibly stable. Once formed, they can survive for millions of years, drifting through space, getting incorporated into new stars and planets, carrying the chemical signature of their violent origins. PAHs have been detected in comets from our solar system. They've been found in meteorites that fell to Earth. They exist in the interstellar medium, the space between stars, in enormous quantities. In fact, about 10 to 20% of all carbon in the galaxy exists in the form of PAHs. That's an astonishing amount. Billions upon billions of tons of complex carbon molecules floating in space. When these molecules get incorporated into comets like 3i Atlas, they become time capsules, fossils from the ancient star-forming environment. By detecting and analyzing them, we can learn about conditions that existed millions or even billions of years ago in regions of space we'll never visit. The connection goes even deeper. Every atom in your body, every carbon atom in your DNA, every oxygen atom you breathe, every calcium atom in your bones, was created inside a star. Not our sun, an earlier star. A star that lived, fused hydrogen into heavier elements, and eventually exploded in a supernova, scattering those elements into space. Those atoms drifted through the galaxy. They were incorporated into a new molecular cloud. That cloud collapsed to form our sun and solar system, and eventually, through billions of years of chemistry and evolution, some of those atoms ended up in you. You are literally made of stardust. Carl Sagan said it. Neil deGrasse Tyson repeats it. And it's not poetry. It's physics. It's chemistry. It's documented fact. And 3i Atlas? It's made of the same stuff. Atoms forged in a different star. But atoms nonetheless. Carbon, oxygen, nitrogen, iron, silicon. The same elements that make up Earth, that make up your body, that make up everything you've ever touched or seen or known. The comet is a direct physical, material connection to another planetary system. It's not an abstract concept. It's not a theoretical possibility. It's a real object carrying real atoms from a real place that formed around a real star. And by studying it, we're learning about the universality of chemistry, the connectedness of matter, the shared heritage of everything in the galaxy. Each visitor is an ancient letter, written in dust, carried by time and read only once. As 3i Atlas continues its journey outward, past Earth on December 19th, growing fainter with each passing week, the atoms and molecules it's releasing into space will become part of the local interstellar medium. The water vapor, the carbon dioxide, the complex organics, all of it will disperse, spread out, mix with the existing gas and dust between stars. And someday, millions of years from now, that material might be swept up by another collapsing molecular cloud. It might be incorporated into another star, another planetary system, maybe even another Earth, another ocean, another cell, another mind wondering about the universe. The cycle never ends, the conversation never stops, and we're lucky enough to be alive at the exact moment in cosmic history when we can finally read the messages. But every message has an ending. Every letter gets read and then filed away, and every visitor eventually leaves. The Sleepy Planetarium closes her journal. It's 3 a.m. The telescope dome is cold. The coffee is lukewarm, but the data is good. Another night of observations captured. Another set of measurements added to the growing archive. 3. I-Atlas is fainter now than it was yesterday, and tomorrow it will be fainter still. This is the nature of astronomy. You chase dim lights through the darkness, knowing they're always slipping away. 3 have come, 3 confirmed, 3 documented. Oumuamua in 2017, arriving like a mystery wrapped in acceleration. Borisov in 2019, familiar and reassuring. And now 3i Atlas in 2025, fragile and fragmenting. 3 tokens of a vast unseen population. 3 samples from the cosmic flow that surrounds us constantly. But we know the truth now. We know about the 10,000 objects passing inside Neptune's orbit every single day. We know that our solar system is not isolated. We know that the galaxy is filled with wanderers, debris, messengers, material exchange happening on scales we're only beginning to comprehend. The 3 we've discovered are just the ones we happen to notice, the ones that came close enough, the ones that were bright enough, the ones that passed during a time when we had the technology to detect them. Think about all the centuries humans have looked at the sky without knowing these visitors were passing by. Think about all the objects that passed in the 1800s, the 1700s, the Middle Ages, ancient Rome, the Stone Age, invisible, unnoticed, but always there. And think about the future, the discoveries waiting to happen, because our ability to find these objects is improving rapidly. The Atlas survey that found 3i Atlas is just one system. There's also the Zwicky Transient Facility, the Pan-STARRS surveys, the Catalina Sky Survey, and coming soon, the most powerful asteroid hunting system ever built, the Vera C. Rubin Observatory. The Rubin Observatory, located in Chile, will begin full operations in 2025. It has an 8.4-meter primary mirror and a camera with 3.2 billion pixels, the largest digital camera ever constructed for astronomy. It will photograph the entire visible sky every few nights, creating a continuous movie of everything that moves or changes. Asteroids, comets, supernovae, variable stars, and interstellar visitors. Astronomers predict the Rubin Observatory will detect 1 to 2 interstellar objects per year, not once per decade, not once per generation, multiple times per year. The era of lucky glimpses is ending. The era of systematic detection is beginning. We're about to go from knowing 3 visitors to knowing dozens, then hundreds. Each new detection will add to our understanding. Each new spectrum will reveal composition. Each new trajectory will point backward toward regions of the galaxy. Each new object will be another data point in the cosmic census, and patterns will emerge. Statistical patterns, directional preferences, velocity distributions, chemical trends. By analyzing these patterns, scientists will be able to map the local interstellar medium. They'll identify streams of objects moving together, debris from the same stellar ejection event. They'll trace paths back to specific star-forming regions. They'll characterize the sun's motion through the galaxy relative to the local standard of rest, the average velocity of stars in our neighborhood. This is the dream of the modern astronomer. Not just to discover one object, but to discover enough objects that you can do statistics, that you can test theories, that you can make predictions, that you can truly understand the process. But for now, there's still work to do with 3i Atlas. The comet re-emerged from behind the sun in early November 2025, becoming visible again in the pre-dawn sky. Astronomers around the world immediately turned their telescopes toward it. Michael Yeager photographed it on November 8th, capturing a visible tail stretching behind the nucleus. The Virtual Telescope project in Italy imaged it on November 5th, confirming its diffuse cometary appearance. As of November 7th, 2025, 3i Atlas is around magnitude 9.7. That's bright enough for medium-sized amateur telescopes in dark locations, bright enough for dedicated observers to see with their own eyes, a visitor from another star visible in backyard telescopes. Think about that miracle. But it's fading fast. By December 2025, it's expected to drop below magnitude 12. By early 2026, it will require professional telescopes to detect. By mid-2026, even the largest observatories will struggle. And eventually, it will simply disappear. Not because it stopped existing, but because it moved too far away, because the light reflected from its tiny, fragmenting nucleus became too faint to distinguish from the background glow of distant galaxies. The Hubble Space Telescope is scheduled to monitor 3i Atlas on its way out of the solar system, watching the fragments separate, watching the coma disperse, watching the tail fade. These final observations will tell us about the end stages of cometary disintegration, what happens when an object that survived millions of years in frozen silence finally breaks apart under solar heat and then returns to the cold. The James Webb Space Telescope will observe it again in December 2025 after perihelion, using its infrared instruments to detect molecules that would be invisible to optical telescopes, measuring temperature gradients across the coma, analyzing the composition of individual fragments, squeezing every possible bit of data from this rare opportunity. NASA's Parker Solar Probe, which orbits incredibly close to the Sun, had a unique view of 3i Atlas during its perihelion passage. From Parker's perspective, the comet appeared against the backdrop of the Sun's outer corona. This unusual geometry allowed observations impossible from Earth. The data is still being analyzed. The results will be published in scientific journals over the coming months. The ESA's solar orbiter, also studying the Sun, captured images during the same period. The GOES 19 weather satellite, which monitors Earth's atmosphere, happened to catch the comet during solar conjunction on October 21st, 2025, one of the few instruments that could see it while it was behind the Sun from Earth's perspective. China's Tianwen-1 orbiter, currently circling Mars, photographed 3I Atlas as it passed near the red planet in early October. These images from Martian orbit provide a different viewing angle than Earth-based observations, helping triangulate the comet's exact position and refine its trajectory. The Europa Clipper mission, launched in October 2024 and currently en route to Jupiter's icy moon, has also been taking distant observations of 3I Atlas, as have the Lucy and Psyche missions, robotic spacecraft exploring asteroids in Jupiter's orbit. Even missions not designed to study comets are contributing, because opportunities like this are too rare to ignore. This is what makes 3I Atlas so important. Not just what we learn from one comet, but what we learn about how to observe the next one, what instruments work best, what wavelengths reveal the most information, what observing strategies capture the crucial data. We're learning how to do this science, building the protocols, training the algorithms, preparing for the flood of detections that's coming. On December 19th, 2025, 3I Atlas will pass Earth at its closest approach, 270 million kilometers away, farther than the Sun, safe, harmless, but observable. Amateur astronomers in dark locations with medium-sized telescopes will be able to see it, a fuzzy, faint smudge moving slowly against the background stars, moving away, leaving never to return, and then it's gone. Back into the darkness, back into the silence, back into the pathless flow of interstellar debris. The fragments will continue separating. The coma will expand and thin. The ice will stop sublimating. The object will refreeze, returning to the cold equilibrium it maintained for millions of years. In 1,000 years, 3I Atlas will be light days away from our Sun. In 10,000 years, light weeks. In 1,000,000 years, it might pass close to another star system. Maybe someone else will see it. Maybe they'll wonder where it came from. Maybe they'll name it. Maybe they'll write about it. Maybe they'll feel the same weight we feel, the burden of knowing how vast and interconnected the universe really is. Somewhere in the dark, the fourth is already on its way. We don't know when it will arrive. We don't know how bright it will be. We don't know what secrets it will carry. But it's coming. Mathematics guarantees it. Statistics confirm it. The galaxy is full of wanderers, and some of them are heading our way right now, drifting silently through the void. The astronomer dreams of that discovery, of the alert that will flash across the screen, of the first observations revealing another visitor, of the calculations confirming hyperbolic trajectory, of the spectroscopy revealing alien chemistry, of the whole process beginning again. Because this is what we do now. We watch the sky, we catch the messengers, we read the letters, we learn the language, we join the conversation. It came from nowhere and return to it, as we all will someday. But before we return, we watch, we wonder, we discover, we understand, and we pass that understanding forward to the next generation of astronomers who will watch for the next visitor, and the next, and the next. The universe has been talking for billions of years. We've only recently learned to listen, and what we're hearing is beautiful, and terrifying, and profound. We are not alone in an empty cosmos. We are swimming in a river of matter that connects every star, every system, every world. 3i Atlas is one drop in that river, one messenger in an endless stream, one voice in a conversation that spans the galaxy. And for a few brief months in 2025, we got to listen. The astronomer closes her journal. The dome rotates shut. The telescope powers down. Another night of observation complete. Another piece of the cosmic puzzle documented. Somewhere in the dark, the fourth is already on its way.